Hello everyone. First of all, I would like to thank you for your interest in attending this presentation. My name is Martin Aruyama and today I will be presenting the article Hybrid Recommender System for Educational Resources to the Smart University Campus Domain. This project was developed by the Laboratory of Ubiquitous Mobile and Applied Computing, LUMAC, belonging to the University of Santa Maria in Brazil. This presentation is divided into 4 topics, which will address themes such as the motivating scenario of the project, objectives, operation and architecture of the system, and results obtained so far. First topic is background. The Internet is undoubtedly the most versatile, fast, and practical tool we have today for solving problems and conflicts of interest. It became popular in the 1990s and when several companies realized the potential and started investing in e-commerce and service advertising. In addition, social networks began to emerge and attract the general public, causing the flow of data and active users to grow daily, which often resulted in overloading websites and platforms. The adoption of Internet usage became global, and in 2005, the mark of 1 billion Internet users was reached. And according to Google data, around 8.5 billion searches were processed every day in 2022. Displayed in this graph from our World in Data website is the increase in the number of Internet users on each continent up to the year 2020. Given that this tool has already proven essential in countless tasks and jobs, it is inevitable that the population with access to the Internet will continue to grow gradually in the coming years, and will undoubtedly prove useful in many more applications in the near future. However, the constant and daily increase in the amount of information leads to an overload on websites, browsers, and platforms. This results in 4 main problems. The first one is data integration. Data can be structured in different languages and writing formats. It may also contain irrelevant information, making it challenging to establish a standard writing format for the information added to the Internet. The second one is data visualization. With large amounts of data, it becomes difficult to find relevant information. Searching for specific information among thousands of visually available options is tiring and time-consuming. The third one is real-time processing. The complexity and amount of data affect the analysis time. The more information a certain file contains, the longer it takes to be processed. And finally, data quality. It becomes more challenging to validate the veracity, accuracy, and completeness of data. For these reasons, there was a need to create systems that facilitate user access to the information. Recommendation systems emerged as a solution to this need. According to the article Toward a Deep Recommender System for MOOCs Platforms from 2019, recommendation systems can be defined as follows. Recommender systems are responsible for making predictions about the preferences of a given user over a massive amount of data by calculating the similarity between items, users, and the applicant's interests. These systems look for affinities between information in order to identify possible data to be recommended. The first concept of a recommendation system was presented in the working paper An Algebra for Recommendations in 1990 by a language technology professor at Helsinki University in Finland, Jussi Kargren. Let's take an example of a user who is interested in reading science fiction books, but it is unsure of which one to choose. To explore this literary gem, the user searches on an online book platform that specifies their preference. The platform algorithm searches within its scope and applies various filters to narrow down the search results to a small quantity of books that it believes will be interesting to the user. The system then presents the selected books to the user who can interact with the resources and provide feedback on the recommendations. This type of system hinges on the user information such as interests, interactions, access, and time spent on a particular website to generate predictions about possible features that align with a specific user's interest profile. The more information the system has, the more accurate the recommendations will be. With this in mind, many websites, platforms, and applications adopt these systems to always offer their users what interests them. Some examples of such platforms are food and delivery apps, news and series platforms, social media and relationship sites, travel apps, and also educational websites and platforms. Another research field that has caught the attention of universities is the development of smart campuses. They will be the integration of all kinds of application service systems that create a living environment with intelligent learning and teaching, which is suitable for management, teaching, scientific research, and health, and is also based on Internet of Things, or IoT. Here are presented some of the main features offered by a university that could be considered a smart campus: e-card, energy management, optimization and analytics data center, adaptive learning, smart facilities services, smart transportation, smart classrooms, and security and safety. These are very common points in the university today, but it does not necessarily mean that it must offer these specific resources to its stakeholders. There may be countless others. Here are some examples of the use and application of these resources within a smart campus. The first one is Smart Facility Services, which goes for sports centers, libraries, restaurants, shops, and campus social media. For smart classrooms, we have virtual reality, interactive and collaborative platforms, remote teaching and learning, and also collaborative research. For smart transportation, we have smart parking, tracking of vehicles used on campus, and smart navigation. For security and safety, we have intelligent security and protection systems. For the smart card or e-card, we have access to the classrooms, laboratories, dormitories, and library, such as digital wallet payments and data storage control. For energy management, we have sustainable and smart energy management systems, use of renewable energies, smart lighting, electrical vehicles, charging systems. For optimization and analytics data centers, we have big data centers and use of cloud technology. And last but not least, we have adaptive learning, which goes for personalized teaching methods, specific supplementary courses and disciplines, computerized feeding tests, and also educational resource recommendation systems, such as the one being developed in this project. Now, in this section, I would like to present the techniques and algorithms used in the project, as well as its functioning and architecture. But how do recommendation systems work? How do they know what type of information a particular user will be interested in? Their functioning is associated with filtering techniques, which are algorithms responsible for connecting users, information, and items and determining the similarities between them. There are several types of filtering, with one of the most well-known being content-based filtering. This technique recommends items based directly on the user's interests, characteristics of an item, and similarities between items. Therefore, if a user's interests change, their recommendations will change as well, making it a very dynamic filtering technique. Content-based filtering can generate good recommendations even with a small database, due to its volatility. Let's say, for example, that the user is interested in anatomy, biology, and sports. A dataset contains the 9 items shown in the figure. If the user requests a recommendations, most likely the recommended items will be running, chemistry, and physical therapy, as each one relates to the user's interests. Another widely known and commonly used type of filtering is collaborative filtering. This method looks for the users who share similar interests and generates item predictions for them. Collaborative filtering uses evaluative matrices that record each user's ratings and specific items. Based on this data, it generates recommendations for other users who have not interacted with the same resources. Let's say, for example, that user A is interested in robotics, programming, and rockets, and user B is interested in robotics, programming, and electric vehicles. It can be observed that the users share two of the same interests, therefore they are quite similar, which leads the algorithm to believe that it is possible to recommend items about rockets to the user B and items about electrical vehicles to user A, because most likely they will be interested. Here we have an evaluation matrix consisting of 3 users and 5 resources. For each resource, each user provided feedback to the system indicating whether they like it, did not like it, or not have interacted with it yet. Based on the evaluation of similar users, the system will then make predictions about whether to recommend a particular resource to users who have not interacted with it yet. Combining various filtering techniques into a single algorithm can create a hybrid system that generates more accurate recommendations. This type of system uses 2 or more techniques, enabling the system to overcome the disadvantage or issues of one approach with the advantages of another. For example, the Smart C recommendation system is a hybrid system that employs both collaborative and content-based filtering techniques. In this project system, both collaborative and content-based filtering were used to overcome 2 common issues. The first one is the cold start problem, which occurs where there is insufficient information about a user or resource to generate recommendation, and also limited diversification, which restricts users to recommendations based solely on their interest, leading to a lack of content diversity. The recommendation system of the SmartC platform operates based on user inputted topics of interest, which are keywords that the user must provide in order to receive recommendations. These topics cover a wide range of subjects, such as engineering, programming, electric vehicles, history, Python, architecture, robotics, and many more. To initiate the recommendation process, the following steps need to be followed. Firstly, a new user must register and log in to access the platform. Once inside the system, users should select and save their interests following the provided instructions, thereby creating a user-topic relationship for each interest. After completing this step, user will be redirected to the Recommendations tab, where the filtering algorithm will begin to generate personalized recommendations. The algorithm works with 2 types of filtering. Firstly, if it is the user's first request, content-based filtering is applied. Otherwise, the algorithm will query which filtering technique was used in the last request for the particular user and alternate the use of the other type. When using collaborative filtering, the algorithm searches for all users in the system who share similar interests with the requested user. It then compares their topic lists and ranks the most similar users. Based on the recommendations generated for the most similar users, the algorithm generates recommendations for the requester. With content-based filtering already implemented, the algorithm will first check if the user has any saved resources in their favorites. If there are saved resources, the algorithm will search for related resources based on the user's topics of interest. It will then compare the bag of words parameter of each found resource with the saved resources, increasing the accuracy of the recommendation. If there are no saved resources, the algorithm will recommend a list based solely on the user's topics of interest. The following flowchart illustrates the steps of the SmartC platform recommendation process. The architecture of the project is divided into 3 sections: the user access layer, the recommendation management layer, and the persistence layer. The first layer is the part accessible to users. It is the means by which the general public has access to the platform and educational resources, which can be accessed through mobile devices or computers. The second layer is where the development environment is located. That is, it is only accessible to developers and as system administrators. Here, changes and updates are made to the algorithm and platform visuals. Whenever a user interacts with the system, information will be retrieved from the database and processed in the recommendation management layer, before being returned to the user. Finally, in the third layer is where database is located, containing all the necessary information for the system's recommendations stored in tables. Now, in the evaluation section, the data currently present in the system as well as the results of the recommendation prediction test will be presented. The current dataset comprises content collected from the scope of the Federal University of Santa Maria, including scientific articles, professors, university courses, disciplines, technical courses, and video lessons. The items were identified and crawlers were developed to import the information from the items into the system. There are 189 areas of interest covering topics related to the study fields of one of the university campus located in Cachoeira do Sul, such as architecture and engineering. In addition, there are also 437 educational resources divided into graduate program work, professors, mini-courses, master's course dissertations, research projects, graduate dissertations, research papers, extension projects, general information reports, PhD theses, and media publications. We have an example of the recommended screen on the platform. It presents the options for interacting with a feature and how each feature is displayed for the user. Just below the feature's logo, we have the title and the abstract. Moreover, every feature on the website provides 4 interactive options. These options include View, the Visualize button. This option allows the user to access the complete content of a specific feature. The Rating button. With this option, the user can evaluate the feature using a 1 to 5 star scale. The Favorite button. With this option, lets the user save the feature to their favorite list for the future use. And last, we have the Remove button. This option will cause the specific feature to no longer be recommended to the user. In order to test the efficiency of the system, an accuracy test was performed with fictitious data, in which each educational resource created was related to one of the 10 topics presented in the tables below. Groups of users were also created between 20 and 100 for each individual topic of interest, and groups with 2 simultaneous topics of interest were divided into engineering and each one of the 4 topics: art, science, mathematics, and music. From these relationships, it is expected that the algorithm understands that there is a relationship between users who are interested in engineering and those interested in art, science, mathematics, and music, and recommends educational resources related to these topics for users who only like engineering. This table displays the random quantity of users created for each singular topic of group of topics. Finally, the tables below display the accuracy test results in descending order of the most relevant topics for a user solely interested in engineering. It is evident that following the engineering topics are the topics of art, music, science, and mathematics, proving that the algorithm is capable of predicting potential interests of a user solely interested in engineering. Lastly, we have the article's conclusions, the goals achieved with this project, and future objectives. The Smart C application serves as a tool for the development of smart campuses by recommending educational resources not only for academics but for all university stakeholders, utilizing multiple filtering techniques and libraries in its algorithm. The evaluation results demonstrate that the algorithm is currently capable of generating accurate predictions regarding a user's possible interests even with minimal information provided. As future goals of the project, it is intended to implement a resource evaluation system in the algorithm and make generated recommendations also take this parameter into account. With this, it is expected that the accuracy of the system will increase even further and that the generated recommendations will better satisfy the users. For any inquiries regarding the Smart C presentation or project, please contact the email address below. Thank you so much.